Hello and welcome to video lecture 15, which is going to be all about power in AC circuits. Power is the last topic that we need to cover in AC circuits. So far we've looked at AC circuit analysis and we've understood how to apply all of the DC tools that we knew in the past to AC circuits, and we also learned what can be used directly and what needs to change. The last topic that we need to cover in this area is power. Recall that when you consider a DC circuit, in DC circuit analysis, power is the time rate of change of energy, which can be calculated very simply as the voltage times the current. This is in fact a general statement, and so if you were to look at the power as an instantaneous measure is simply equal to the instantaneous voltage times the instantaneous current. In DC, we simply know that the voltage is a constant and the current is a constant. So it becomes easier to measure. But the way we did this in the past works completely in AC power analysis as well. Now the total energy transferred over a period of time is simply the integral of the power over that time. So the work is simply the integral from time 0 to time t of the instantaneous power. And of course, this definition works just as well in AC circuits as it does in DC circuits. So we've pretty much got a foundation of how we're going to work with this. The last thing that we're going to consider for a moment is the maximizing the power. So we recall that if we have a Thevenin DC circuit and we attach a load to it, then we maximize the power in this circuit by ensuring that the load is equal to the resistance of the Thevenin circuit. Similarly, if we were looking at a Norton circuit, we have a current, we have a Norton resistance, and if we want to maximize the power, we make sure that we attach a loading resistor that has the same value as RS. In fact, when you maximize the power, the load resistance matches, and you'll find that the power in that case is simply equal to either the Thevenin voltage times the Norton current over 4, or if you want to consider the resistor directly, the voltage squared over 4R, or the current squared times R over 4. So we find this using derivatives, and it's a straightforward analysis. When we consider the instantaneous power in an AC circuit, we know that that power is now a unit that changes over time. And we can take a look at this and recognize some of the information that we have. We know that voltage, if you have a single frequency, can be defined as a phasor where we have the voltage amplitude at an angle of phi v, which is simply the phase shift. And we know that that happens at theta rads per second. And if that's the case, we also know that the current can be defined as a phasor, similarly with its own phase shift, and it also operates at the same frequency. Well, if you're going to take the instantaneous power, you're simply going to multiply these two things together. Be careful though. You cannot use phasors to do this. You use phasors to get through the current and voltage information, to get through the impedance, and to find what the currents and voltages are, but you can't use phasors in general for power. Why? Well, very simple. Recall that the voltage is going to be the real part of some complex function. The current is going to be the real part of some complex function, and this is absolutely not equal to the real part of those two functions multiplied together. Now, if we look at the sinusoids pictured above, you can see that the dark blue line is your voltage, the red line is your current, and the cyan line is simply a sinusoid that has no phase shift for reference. The phase shift of your voltage is phi v. So your voltage, when it has a positive number, lags behind the original sinusoid. If you look at the red line indicates your current. And you'll notice that that has a phase shift that is not quite as big. You can actually consider the difference between those two phase shifts, and that difference is a very important number. That difference will dictate what the power looks like. Without any loss of generality, you can actually assume that the phase shift on the voltage is equal to 0 and assume that all the phase shift is in the current. It's simply going to shift the time slightly. So you shift the time slightly by considering a shifted time and look at the structure of the curve. And the structure of the curve you get is down below. It's the black line. Now that's very interesting because you can note that the frequency of the power sinusoid is double that of the voltage and current, which is a rather interesting fact. So you take a look, you see that one period of your voltage and current is in that neighborhood, whereas one period of your power is over there. You also see something interesting over here. All of the sinusoids that are pictured in the original frequency theta t all are symmetrical about 0, but the actual power sinusoid is raised, so its lowest value is a little below 0, its highest value is a little below 1. So it's got a smaller amplitude and a faster frequency. And these are all properties that are very important in terms of the context of what we're going to see. So let's take a look back at some high school trigonometry. We realize that we are going to be looking at the cosine of a phase shift plus a frequency. And that's going to essentially phase shift our regular cosine. And so when we do that, if we want to have any chance of doing any computations, we want to make sure that we're able to take this and split it up. Well, we do that by looking at the two-angle cosine formula. And in fact, all of the double angle formulas that we're going to be using are summarized on this page, and we're going to be looking at pretty much all of them in order to do our computation. So let's go back to the power. Our power is equal to our instantaneous voltage times our instantaneous current. And what we can do is we can take this and do a little bit of manipulation with trigonometry. So the power is equal to the amplitude of voltage times the amplitude of current. And then what we're going to do is we're going to take our double angle formula and expand out. So we end up with the cosine of the phase shift times the cosine of the moving sinusoid minus the sine of the phase shift times the sine of the moving sinusoid. And this is simply, and then we multiply that by the original cosine of theta t, our moving sinusoid. So we notice that all of this comes from our trig. It's the multi-angle cosine formula. So looking at what we have above, we can actually clump things together and we get the voltage amplitude times the current amplitude times the cosine of our phase shift times cos squared theta t minus the voltage amplitude times the current amplitude times the sine of the phase shift times the sine of theta t and the cos of theta t. And in fact, each of the two formulas that we just see on the right and left here can be expanded for double angles. So we expand this for our double angle cos, and we expand this for our double angle sine. As we do that, what we end up with is that power is equal to VA, the two amplitudes divided by 2, times the cosine of the phase shift, times 1 plus the cosine of 2 theta t. And now here is where we see that faster sinusoid coming in. And the 1, that's where we see our offset. And then working on the other side, we have VA, our two amplitudes divided by 2, times the sine of our phase shift. And we plug in the double angle formula on this side, we simply get the sine of 2 theta t. So we see that both the moving sinusoids in here are double the speed, and there is an offset, and while we work with that expanded double angle formula, we actually reduce our amplitudes in half. So recall that for any source for a fixed sinusoidal frequency, we can get a relationship between the voltage and the current through the angle of the impedance. So if the voltage is actually VA, an amplitude of VA with a phase shift of phi V, and the current has an amplitude of IA with a phase shift of phi I, then we know that the equivalent impedance angle is the difference between those two, and we've simply been denoting that as phi VI, which is going to be what we use. These two equations are critical, and they're going to form the basis of pretty much everything that we do in power. So we want to make sure that we have a good idea of what they are and how they're going to be working. So in summary, we see that we have three standard types of elements. We have resistors, capacitors, or inductors. Resistors simply dissipate energy, and so the power that they use is always a positive number. On the other hand, in an energy storage element, they supply and dissipate power. So they both supply and dissipate. They both have the structure of the instantaneous power is equal to, and we have a difference in sign, but other than that, the amplitude of the voltage times the amplitude of the current over 2 times the sine of 2 theta t. For both of them, we see that the sinusoid is double the speed of the original sinusoid. And there's one more important thing that we can look at. We see that these are cyclical. Not only are they cyclical, if you consider the work over an entire period, then you take the integral of the instantaneous power over that entire period, that's going to be equal to 0. They're cyclical with an average power usage of 0. What happens is that in half of a cycle, they're dissipating power, in the other half, they're supplying power. So essentially what a capacitor and an inductor do is they charge up and then they release that charge in order to supply power. They're constantly, when working with a sinusoid, taking in power, charging, and then supplying power. And that's actually quite useful because what they can do is they can help alleviate power needs in a circuit sometimes. So let's talk about the average power and what happens with the sinusoids. In general, power for absolutely anything that we're looking at, any source or any element, is simply equal to VA IA over 2 times the cosine of the phase shift between the voltage and the current in that element times 1 plus the cosine of 2 theta t minus VAIA over 2 times the sine of that phase shift times the sine of 2 theta t. Now, we know that if we want average power, we simply look at the work. We have to take the integral over an entire period of the instantaneous power. And when we do that, we have a lot of interesting things that we figured out. First of all, we figured out that for a resistor, the angle between the two is 0. We figured out that for an inductor, the angle between the two is plus 90 degrees. And we figured out that for a capacitor, the angle between the two is minus 90 degrees. In general, when you're looking at a source, the angle between the two is going to be the angle of the impedance. So for a source, oops, and so the impedance that you have in a circuit that is seen by any source is actually a very, very important thing for that. Now, if we take a look at the equation we have here, we're going to regroup it into 3 parts. P of t is equal to a fixed or DC part, VA times IA over 2 times the cosine of that phase shift angle. And then there's going to be a secondary part that looks at that same basic value VAIA over 2 times the cosine of the phase shift, but is multiplied by a moving sinusoid of cos 2 theta t. And then we have the minus VAIA over 2 sine of the phase shift term times the sine of 2 theta t. If we want to understand the impact of the sinusoids on average power, we take the integral of each of these parts. And now the integral of, I'm not quite sure why that highlighter keeps turning on. And now the integral of the first part has a value of VA IA over 2 times the cosine of the phase shift, that is just the constant that it was pre-multiplied, multiplied by the actual amount of time there is in the period. On the other hand, if you're looking at the other two parts, they have moving sinusoids, they're symmetrical. So if you look at the area under the curve, the area above and the area below actually cancel out, and each of these, their integrals over a period, and only if you take them over an entire period obviously, are equal to 0. What does that tell us? That tells us that that first term is the only source of average power dissipation, and that power dissipation has to come from some resistors, because only something with some resistance has a real value in the impedance. The real value in the impedance is what's going to get you to that cosine of 5 VI. And of course, if you think about this cosine, that's simply the ratio of the real part to the entire part. So that cosine, that makes it very clear. The more real part you have, the bigger that is. The less of a real part you have, the smaller that's going to be. So if we take a look at an average power in our different circuit elements, there's three basic circuit elements that we have: our resistor, capacitor, and our inductor. And of course, there's also the sources themselves. For the resistor, we can summarize for each of these the power in them. So the power instantaneously in a resistor is equal to VA IA over 2 times the cosine of the phase shift, but of course that's just equal to 1 times 1 plus the cos of 2 theta t. For a capacitor, our instantaneous power is simply equal to VA IA over 2 times the sine of the phase shift, but of course that's just equal to -1, which gives us our positive sign, times the sine of 2 theta t, the moving part. And lastly, for an inductor, looks a lot like a capacitor. We have the same thing with a minus sign, so minus VA IA over 2 times the sine of 2 theta t. And if we want to take each of these and we want to look at the total energy used, or the work for a resistor is equal to this integral over 1 period. That's simply equal to VA IA over 2 times the length of the period, where in general, just realize that that period is equal to 2 pi over theta. On the capacitor and inductor, on the other hand, if you look at the work and you take those integrals, well, you have something that's perfectly symmetrical, and in both cases, that integral simply gives us a value of 0. So, in summary, the work for a capacitor or an inductor over an entire period is just equal to 0. They're both supplying and dissipating energy, so they collect energy and then they give it back out, and they do that in equal proportions. On the other hand, a resistor is a purely energy dissipating element. The work over an entire period is just VA IA times pi over theta. And so we see that we can summarize the average power for these straightforward elements very easily. And the only thing we actually need to do hard work for when we look at power is we need to work at understanding the power in our actual sources. And of course, the work in our sources is straightforward, because in that case, in a source, we use the phase shift angle between the voltage and current in the source in order to go back to our longer, fuller formula on the previous page. Now, it's very important to understand what power does, and in general, we want to make sure that we maximize average power. Over any given cycle, the work from our source is equal to VA IA over 2 times the cosine of that phase shift angle times the period. If we want to maximize this, notice that our maximum power can only happen when that cosine is equal to 1. In other words, when this is equal to 0 degrees. In other words, maximum power happens when it happens when our voltage and our current are in phase. So you'll notice that there were a lot of questions previously in the AC work on when something is in phase. We considered the resonant frequency. We talked about all those important things. Well, the reason they're so important is because when we have maximum power, that only occurs when things are in phase. So let's talk about this cosine of our phase shift for a minute. Recognize that sometimes you might have a situation where the amount of power that an element needs in order to operate properly is fixed. Well, if that's the case, and you have VAIA times the cosine of the phase shift in your source, then you're only going to have efficiency as long as that cosine is 1, or as long as in the source the phase shift is as close to in phase or as little as possible. Power requirements are very often predefined, so this is a realistic thing to do, and this is important. When signals are not in phase, you're going to need more voltage to deliver the same amount to the load. So that's a really, really important point. And the closer that a signal is to in phase, the closer you're going to be to optimizing your power. So think about this for a minute. You have elements. You have either a resistor, capacitor, or an inductor, and then you have sources. You have either a voltage source or a current source, which I've drawn kind of sideways over there. Well, if you think about this, the voltage-current relationship in any element is fixed by the element. We've already seen that. Resistors are in phase, capacitors are out of phase, inductors are out of phase. But the point is not so much about those elements. Any element is going to have whatever power requirement it needs, and it's going to work within its own. And you realize that any resistor is going to simply dissipate power, and you need to ensure that you supply enough power to that resistor in order for it to operate the way you need it to. For example, you need to give your furnace enough power to warm up your house in the middle of winter. You need to give your refrigerator enough power to cool the food inside of it. You need to give your cell phone enough power to charge the battery. All of those things are going to be somewhat fixed. The capacitors and the inductors, they're the energy storage elements. They can help us work more efficiently. But at the end of the day, the importance of the phase is really in the source. And the reason that the importance of the phase is in the source is because we can see that if in the source our voltage and current are as close to in phase as possible, then the power requirements are going to be as close to optimal as possible. What ultimately happens is those elements, those resistors, they need a certain amount of power to operate properly. But if you're out of phase in your source, then you need to be supplying so much more voltage in your source in order to get to the same current, in order to get to the same power. And that's the key in terms of the importance of phase. It's very important in your source to keep things as close to in phase as possible so that you're able, as much as possible, to maximize the power efficiency of your system. Now let's go back to instantaneous power for a minute. If we take a look at our original power equation, we see that there's some important key factors. First of all, the two amplitudes of our voltage and current. Second of all, our actual phase shift. And we see that we can take this information and we can rewrite this. We rewrite it as the two amplitudes divided by 2 times the cosine of that phase shift, and that's a fixed constant. We're going to call that constant P, and that is going to multiply by 1 plus the cos of 2 theta t, and then we subtract off VA IA over 2 times the sine of that phase shift, and multiply that by sine of 2 theta t. We're going to take the second constant that we have here, we're going to call that Q. P is just our average power, and it's calculated in watts. Q, on the other hand, is something called reactive power. And the reactive power, although it comes in the same equation, we use a different unit for it. This is called VARs, which stands for volt amp reactive. And essentially what that tells you is that you took a voltage, multiplied it by a current, and its reactive power, which means that it is next to a sinusoid that is moving and there is no DC component to it. If you regroup these, then that first term, which is just P, is your DC component. And if you clump the other two terms, you have P times your cosine of 2 theta t minus Q times your sine of 2 theta t, and those two terms form an AC component because they are always cyclical, and the average of those two terms is equal to 0. So again, you have P over here, you have P over here, and you have Q over here, and that gets us to a breakdown of our instantaneous power. Now, the only reason we want to do that is because we want to consider the average power ultimately. So when we take a look at this, we have our P term up here, our Q term over here. We realize that P is our average power, Q is our reactive power. Our total instantaneous power can be broken down in this way. And if we look at the work is simply equal to the integral of our instantaneous power over an entire period times dt. And of course, that's equal to P times the integral from 0 to Tp of 1 plus the cosine of 2 theta t minus Q times the integral from 0 to Tp of the sine of 2 theta t. This integral is equal to 0, and our first integral has two components to it. The first component gives us a value of Tp. The second component leads to 0. In other words, the work, as we've calculated several times, given that integral, is simply equal to P times the length of time in the period. And in fact, essentially the average work that's done is going to look at the amount of that actual average power P multiplied by the amount of time that it has been active. So that over there is a very critical and important formula. Now let's take a look at that average power one more time. We notice that we always see this term VA IA over 2. Well, VA is just your maximum or peak amplitude of voltage. And amplitude, of course, is spelled in a way that is more like that. IA is also your maximum or peak amplitude. Now, typically the maximum or peak amplitude isn't actually the most useful value, and you can see that by looking at the average. You see that you're always looking at VA IA over 2. And the reason for that average is the fact that you never quite hit a full sinusoid except at one point in the cycle. In fact, if you want to have a bit of a better understanding of a sinusoid, you realize that the average for each of these sinusoids is that peak value divided by the square root of 2. And so we consider the RMS value, and RMS is actually what usually is listed. So when you look at your listings for energy and power on your outlets or in other places. You're not being given peak amplitude when you deal with AC signals. You're being given RMS values. The way to relate the two is very, very easy. If you want to get back to your peak amplitude, the peak amplitude is just equal to the RMS value times the square root of 2. And the average power is more simply stated by the RMS values. So if you want to look at RMS values in terms of average power, P is equal to those two RMS values times the cosine of the angle between them. Q is equal to those two RMS values times the sine of the angle in between them. So if you consider power and you look at the AC component of power, the AC component of power is simply equal to P times the cosine of 2 theta t minus Q times the sine of 2 theta t. What are P and Q? P is just VRMS, IRMS times the cosine of the phase shift, and Q is just equal to VRMS, IRMS times the sine of the phase shift. So this is really just another notation. It's an understanding, but it's important because usually AC power actually uses RMS in order to define power. So we've looked at this a bunch. We've seen some important things, and we want to bring out some of this. Let's take a look at our AC power. This should remind us of something. It's not quite the same, but it looks a lot like our phasors. Let's talk for a minute about complex power. Now just be careful because power is not actually a phasor value. It's just a useful way to notate the information that we have. And that's different from voltage and current in an AC circuit because those actually use phasors in order to do the calculations. In power, we can keep track of power based on phasors and based on this information, but we don't actually have phasors and we can't actually do all of our calculations this way. So remember that e to the j psi is equal to the cosine of psi plus j times the sine of psi. So let's try and use this to keep track of AC power. Remember that in AC power, we have P times the cosine of 2 theta t minus Q times the sine of 2 theta t. And this is almost but not quite complex. There is no j over there. So therefore, it's not complex. But if there was a j, then it would be complex. In fact, we can actually use complex notation to do some of our power, to look at some of our information. So let's consider voltage as a phasor, and let's consider current as a phasor. But be careful, we're doing something different than we usually do in AC circuits. We're using voltage and current in their RMS values instead of in their peak values. Whenever we analyze circuits, we need to use the peak values. Whenever we use complex power, we consider the RMS values. Well, if you consider that and you notice that there's a minus sign over here, then we have a way of notating our power as a complex number. So pretend that that was a complex number. Pretend we had a j in our AC power. Well then, if we took V and we multiplied it by the complex conjugate of I, we would get P minus JQ. And that, in fact, is a way to notate the power where P is simply equal to the real part of this complex power, Q is simply equal to the imaginary part of this complex power, and then if you wanted to note our AC power all together, you would note that PAC is equal to the real part of S plus the imaginary part of S, where, be careful, the reason I added as opposed to subtracted is because that minus sign is already taken care of in the complex conjugate. So basically, this is not a groundbreaking change in computation or anything else. This is simply a new way of phrasing the power. But this new way is very important because it helps us understand some of the very critical things that we need to in the context of power. So let's look at something that we call the power triangle. The power triangle is simply a way to keep track of the different parts of our power, and essentially we take a look at that complex number, that S, and we can draw that out. So drawing our complex plane, we have our real axis, we have our imaginary axis, and we realize that we've written down S as equal to P plus JQ or P minus JQ, depending on whether that's a positive or negative number. So if we're going to do that, P is just our average power. We put that along the real axis. Q, even though it's not really an imaginary number, gets put on the imaginary axis. And sometimes that number is positive, sometimes that number is negative. If we do that in this way, then we have our complex vector S. And remember what each of these are. Our average power is simply equal to VRMS times IRMS times the cosine of that angle. On the other hand, our reactive power Q is just equal to VRMS times IRMS times the sine of this angle between the voltage and current. So if you look at that, then you realize that you have your very classic triangle where the magnitude of our complex power is just going to equal VRMS, IRMS. And if we want to take a look at that reactive part, it's on the right. If we want to look at the average part, it's on the left. Those simply relate to the bottom and top of this triangle. And of course, that means that the angle in this triangle is just our phase shift. And if we had, on the other hand, drawn it on the lower side, we would still have that same phase shift angle in there. In order to really understand the importance of the power triangle, we're going to go back for a minute to the instantaneous power. In order to fully understand the benefit that the power triangle has in terms of analysis, let's take a quick look back at the original equations. We see that the instantaneous power is equal to VRMS IRMS times the cosine of the phase shift between the voltage and current, multiplied by 1 plus the cosine of 2 theta t, and then we subtract off VRMS IRMS times the sine of the phase shift angle, multiplied by the sine of 2 theta t. This really breaks down into two parts. So we have this part, which is P, and this part, which is Q, and what we're actually left with is that P of t, the instantaneous power, is equal to P plus P times the cosine of 2 theta t minus Q times the sine of 2 theta t. Now, as far as that instantaneous power goes, the first part is a DC part, which we don't consider here, and the second part is what we've used in order to construct our power triangle. We notice that when we look at the two parts here, the bottom gives us, if we take these values and we look back, at our power triangle, we see that the complex number that is encompassed by the total reactive power goes on the hypotenuse. Our average power goes along the bottom of the triangle, and our reactive power goes along the side. And this is how we get back to all the important information. And of course, that leaves us with an understanding of this angle, which fits right into there. Now, this is really important in general because it gives us a way of understanding the different relationships that happen between here. We see that the larger that phase shift, basically the larger the reactive power in that triangle becomes. We also know that for certain elements we have values that give us extremes. So for example, when we look at the phase shift in a resistor, there's 0 degrees. That's an extreme where all we have is average power. when we look at the phase shift in a capacitor, we have negative 90 degrees. When we look at a phase shift in an inductor, we have positive 90 degrees. Those are both extremes in which we have only reactive power. Now, generally, if you go back to the structure of this triangle, then you learn a lot of information based on understanding where you are within this triangle. If you're on the upper side in the first quadrant, we consider this lagging. What does that mean? It means that the phase shift of the voltage is greater than the phase shift of the current, so therefore we have a positive value for the difference between them. On the other hand, if we're in the lower half of this, we talk about leading. What does that mean? That means that the current leads the voltage. So we have the phase shift of the voltage is less than the phase shift of the current. Typically, inductors fall into the upper category and capacitors fall into the lower category. Now, when we look at most residential and industrial power, we talk about lagging power. So lagging is the more common power that we have, and essentially all of this leads to the basic structure. Now, why is this important at all? Let's talk about that complex number. The complex number, if we look at its magnitude, that gives us the apparent power. That's simply the RMS value of voltage times current. And when you look at what you actually have in a system, you have that apparent power times this cosine of the phase shift between them. Well, if you take the power factor, that's simply the ratio of the actual average power to the apparent power, you get back this cosine. And this cosine comes back, if you recall a couple slides earlier, to the efficiency of your system. You want that cosine to be as close to 1 as possible, otherwise your system is less efficient. So let's review where that angle comes from. Complex power comes from the concept of complex impedance. Complex impedance comes from AC signals. So we know we have Ohm's law for impedance and for phasors. When we look at a system that is operating with a single sinusoidal voltage or current source, then we understand that Ohm's law in the phasor context can tell us what the relationship is between the voltage and the current. And it's simple. The relationship is about the load. So consider a load. When you consider that load, let's just switch back to red. When you consider that load, you know that you can easily see the phase shift angle. The phase shift angle comes from the angle in the load. Now, when you do that, if you want to get back to this complex power or this complex representation of power, well, all we really have to do is take a look at the phasor for voltage, the phasor for current, and you multiply the voltage phasor by the complex conjugate of the current phasor. Now that's interesting because V, if you look up above, is simply equal to the impedance times the current phasors. So you can actually expand that out and you end up with your impedance multiplied by your complex conjugate of your current times your current itself, which simply gives you your phasor for your load multiplied by the magnitude of your current phasor squared. Well, what that really means is that the only thing you need in order to understand that phase shift angle is you need to understand the complex impedance of the load. Well, if you break it down, you know that resistors will always have real impedance or real numbers, and that gives you resistance. And if you have capacitors or inductors, they have a reactance, they have a purely complex impedance. Well, essentially, whenever you have a load, you have a complex circuit put together. It has resistance components to it, and it has reactance components to it. And by the time you're done and you put it all together, you're going to end up with this simple relationship. And you know that the angle of your impedance is simply equal to the tan inverse of the imaginary part over the real part. Well, that angle is actually the same angle as your phase shift between your voltage to current. So if you take a look at this information, your complex way of describing the power in your load is simply equal to the magnitude of your load times the magnitude of your current squared times the cosine of that phase shift plus J times the sine of that phase shift. And if you do that, you realize that that phase shift, like I said, is just equal to the tan inverse of imaginary over real. The complex power is what we look at when we consider the reactance and when we consider the average power, P, and the reactance, Q. So those two parts together are critically what we have, and you can go right back to here and you get your average power straight from this equation. That average power brings us directly into efficiency of the system. So we'd like to know how efficient a system is, and simply put, we've already seen this, a system is most efficient when it is in phase. What does that actually mean? Of course, you can't change the phase of your components. Your resistor will always have real in-phase components. Your inductor and your capacitor will always have out-of-phase by 90-degree components. But what's important is what the source sees. So you assume that you have a load. That load has to require an average amount of power, and you want to know if that load is given what it needs, what will the source see with respect to this? So the power that the source sees is simply going to equal the magnitude of the impedance times the RMS value of the current squared times the cosine of that angle between the load. Notice that this is simply equal to phi of VI. It's exactly the same thing. That angle in your load is equal to exactly the same thing that the power sees. So that maximum power is going to happen whenever this is equal to 1. What does that mean? Here is your load. Your load sees a complex impedance ZL. Your load has a voltage. That voltage is fixed. So we're going to give that voltage a value of VRMS with a phase shift of 5V. Now, we can from here very easily calculate what our current is going to be, and our current is what's drawn by the load. And you realize that the current and the voltage, they're dictated directly by the load. The voltage is what you start with, the load is what you need to supply, and the current is drawn by the load. So from the perspective of either the load or the source, you're going to get the same thing. VRMS with an angle of 5V divided by the load at an angle of 5VI is equal to IRMS at an angle of phi I. So you've got your phase shift of your voltage, your phase shift of your current, and of course the difference between them is going to be exactly what the complex impedance angle of your load is going to be. So what does that tell us? We're going to know that in your source, you have VRMS, IRMS times the cosine of that angle between them as the power that is going to be seen from the voltage current relationship. Well, if you want to look at your load, you get the same information, and you can look at it either in terms of voltage or current. So in your load, you can either write V squared RMS over ZL times the cosine of that angle is equal to the power, or you can similarly, and these are the same, write that the load power is equal to I squared RMS times ZL times the cosine of the angle between them. So these are the perspective of your load. The above is the perspective of your source. And of course, your source powers your load dissipates the power. They're going to be the same. So now where does all this take us, and why are we basically repeating the same thing over and over? Because we want to understand the requirements. Our load has a fixed requirement. So our load needs a fixed amount of power. We also know that our voltage is what's supplied and our current is what's drawn. Well, if we know that we have a fixed amount of power necessary by the load, then essentially that dictates the voltage requirement. And if you take a look at that equation and rearrange, you'll see that V squared RMS is equal to that requirement times the magnitude of the impedance divided by the cosine of that phase. And so the smaller that cosine is, in other words, the more out of phase those two are, the bigger of a voltage we're going to need to supply to our load in order to satisfy our power requirement. And so this is really what it's all about. It's about satisfying the power requirement. And the punchline is essentially that the smaller this is, so the smaller that cosine is, what'll end up happening is the more out of phase those two signals are, so the smaller the cosine, the more out of phase the voltage and current are, the more voltage we will need to supply to get to our power requirement. And that ultimately is the punchline, that we want to minimize the voltage we need to give out in order to satisfy our power requirement. In order to minimize that, we want an efficient system. In order to have an efficient system, we hope that the voltage and current are as little out of phase as possible. Now that may almost seem like a good joke, because at the end of the day, we have a source. It supplies the voltage, which supplies the power. We have a load. That load has a power requirement. And the load has whatever structure it has. We can't change that. So you look at this and you say, okay, that's nice. We want to talk about efficiency. We can look at efficiency by understanding the phase shift between the voltage and the current. But it's kind of fixed based on the structure of this circuit. And that's where we get to the concept of a power factor correction. So let's consider a load. Here we have a load. It has a value of V. We're going to take that value of V, we're going to give it in RMS, and we're going to assume that we, start out with this, but we have the ability to change that voltage. We then talk about our load. Our load has a fixed requirement. That requirement is going to dictate something about the current that goes through it and what is important within that. So we take our load and we connect it to our voltage source. And if this is all we're doing, then there's not much we can do to change the angle. We're basically set with a voltage current angle and we're stuck with what we have. But here's an interesting idea. Let's assume that that load was inductive. In other words, the Q was a positive number. And now let's put a capacitor in series. That capacitor in series now draws a second current. That second current is a purely capacitive load, And so what that means is that there's going to be pure reactance. There's no average power that is drawn by this capacitor. The capacitor is going to simply draw a very fixed amount of current. So let's look at each of these. When we add the capacitor in parallel, we realize that the impedance of the capacitor is equal to minus J over theta C. What does that mean? That means as a phasor, if we look at this, we're going to have 1 over theta C with an angle of minus 90 degrees. All right, now let's talk about our original load for a minute so we understand what that does. In our original load, our loading current is simply equal to the voltage of the source over the magnitude of the impedance with an angle of minus phi L, where this is simply equal to the loading ratio between complex and real. So if we take a look at that, let's talk about the power. The power that's drawn by the load is equal to VRMS times the complex conjugate of the loading current, and that simply gives us a real part of power, that's the average power, plus a complex part. Now remember, it's not really complex, it's just a way of notating it, but it helps us understand what we actually need from the source, times Q. And basically, these things are fixed. We can't change P and we can't change Q. Now let's go back for a minute and look at our capacitor. The current in your capacitor is equal to the voltage of the source divided by the impedance of the capacitor, and we've already figured out up above that that's just equal to minus J over theta C. So this is simply equal to theta times C times the source voltage at an angle of plus 90 degrees. If we want to talk about the complex power from here, not quite sure why it keeps doing that. If we want to talk about this complex power, then the complex power is equal to VC times IC star. Of course, VC is just the same source, so it doesn't change, and that's going to be the RMS value. This is equal to theta C Vs squared at an angle of minus 90 degrees, which means that all we're going to see from our complex power is equal to minus J theta C Vs squared. So it appears that we have a power factor that comes from the load and a power factor that comes from the capacitor, and we have more things than we started with. But do we really? Has this improved our power or has it made it any worse? Let's talk about the new power factor that comes at the load. Well, this is simply equal to the voltage at the load times the current through the load, which is IS, in complex conjugate. Well, if you think about this, that's straightforward. IS is equal to IC plus the original load. So what is this new power going to be? This is just equal to Vs times the load in complex conjugate plus the capacitor current in complex conjugate. But hey, if you take a look at this, this is just the old loading plus the new capacitor. And if you look at the individual pieces, we know what the old part was. That was P plus J times Q. And now if we add in the new part, we subtract off, that's a Q, not a theta. Let's make that a little bit neater. If we subtract off the new part, that's the capacitor part. And in fact, check out what we just did. Our new capacitor, our new system complex power is actually a smaller number than it was before. Let's take a look at the triangles and understand exactly why that is. So let's draw this out. We started out with an original power factor. This is what happened from our load. Our load has P and it has Q. And that gave us our original complex number for our load. In our original complex number for our load, we know that we had our basic VRMS, IRMS times the cosine of this load. Here is that angle. And not anything we can do about this red triangle. This is what's necessary for our system. We have to have the average power P. We have to have the reactive power Q. Now, what we've done is we've added a capacitor. Our capacitor reduces the Q overall. How? It subtracts off J times the capacitive reactive power. So if we subtract that off, what that means is that our new complex power has a smaller value. Why does it have a smaller value? Because we've reduced the angle. We've corrected the power factor. So essentially, we've changed the angle between the phase between the voltage and current at the source by having a capacitor which draws something that works in the opposite direction of what our original thing did. And this is a really, really neat trick because ultimately at the end of the day, the amount of power that our source is going to need to supply is actually reduced. Why is it reduced? Because the capacitor is an element that can absorb the power that is not being used properly and then put it back into the system when it's needed. And so the capacitor corrects the power issues that we see so that we end up with an improvement in our overall system. This improvement is actually quantified by this power factor correction factor. And so if we look at that, let's look back at our original system. In our original system, if all we had was the original load, we've already calculated that V squared RMS, the amount of voltage necessary to power the load with that fixed power requirement, is calculated by taking a look at the power requirement, multiplying the impedance, and dividing by the cosine of the load. Now, how have we improved this? When we've added the capacitor, now V squared RMS is equal to, and we've got the same power requirement, the same load if we look at that factor over there because that comes out of the P, and we divide that now by the cosine of the corrected angle. The corrected angle is the angle that looks different now that we've changed it. And so what we actually see is that this is smaller. We've reduced the amount of voltage that we have to supply in order to get exactly the same power to our load. That's a really neat little. If we want to see what these power factors are and we want to take a look at it, we can note that if we look at the cosine of the old value, that's equal to the average power over the square root of the average power plus the reactive power, each of those squared. And if we look at the new value, the cosine of our corrected power factor, this is equal to P over the square root of, we have the same average power, we haven't changed that, we've just changed the reactive power by subtracting off part from the capacitor, and that gives us our new ratio. And just realize that those are actually ratios that come directly off of this triangle, so we can read this information straight off of the triangle. So this is embedded in the triangle. So this concludes the information about power. The power factor correction and the information about that is really to help you understand some of the interesting and important things that you can do. There's a few simple calculations that you can look at in order to do this. In essence, just to give you an idea of what we've covered the last section of Chapter 8, which talks about power in AC circuits in general and instantaneous power, and we've looked at parts of chapters 16:1 through 4. We've covered all of 16.1 and 16.2. We do have more to say. We've covered all of 16.1 and 16.2, and we've covered parts of 16.3 and 4, but not the entire sections. Now, what I did want to do with you guys at the end of this lecture is take a little bit of a look at the power factor triangle and the corrections that we get out of here. So I've created a series of graphs that show you a little bit about what's going on in the power. This first graph is a graph which shows you that you have a purely inductive load. You know that it's purely inductive because this is a positive number, so it is a purely inductive load. In fact, it is so purely inductive that the phase angle is 90. There is no actual resistance in the system. When you look at this, you can see the 90-degree phase shift between your current and your voltage. And notice that in all of these graphs, the blue line is the voltage and the red line is the current. And down below, the black line is the power. So when you take a look at this purely inductive load and you look at this, you see, first of all, that the voltage lags the current. You could say the current leads the voltage, or you could say the voltage lags the current. We typically talk about what the voltage does. So voltage lags the current. And that tells us everything we need to know in terms of the power triangle. We know that ZL, that's a Z really, ZL is equal to R plus JX. In this case, there is no R. It's a purely inductive load. And if it's positive, this is inductive. And we talk about inductive reactance being positive. So what does that tell us with respect to the power? Notice that the bottom of the power and the top of the power are roughly equidistant from the zero line, and actually the average power, or the midpoint in that, is equal to 0. So average value is equal to 0. What does that tell us? That tells us that we are looking at something that has a purely complex number. So therefore, P is equal to 0. All of the power comes in a Q factor. Now let's look at what happens if we change up our loads a little bit. And so what I've done is created a series of these graphs for different phase shift angles. This one has a phase shift angle of 60 degrees. And what's really neat is you can see the changes in your power. Your power is now not centered around 0. It actually has a midpoint centered above here. And it goes slightly below 0, slightly above 0. There's still that sinusoidal repetitive nature to it. You also, in all of these graphs, see very clearly that the power has a sinusoid that's double the frequency of the voltage and current. And in this case, you have a reactive load. ZL is equal to R plus JX, where the tan inverse of X over R, leads you to 60 degrees. So there is some real part, some inductive imaginary part. Notice that this is still inductive because it is positive. As these things get more and more in phase, you see the power moving. So now this is slightly below the unity line. This is slightly below 0, but the average power is rising. And that average power is rising as the phase shift gets closer to 0. And in fact, when the phase shift is 0, when we have two systems that are completely in phase, we have the best possible scenario. We have this going up to 1, this going down to 0 but not below, and we have the greatest average power that we can get. So this is average power. And you notice that you never have anything that dips negative. What does that mean? It means this is a purely resistive load. It only dissipates power. And when you have this purely resistive load only dissipating power, you're not wasting power on something that is an energy storage unit, which is going to charge back and forth. And the way to do that, if you think about your power factor and your correction, is you set up a power factor triangle where, to start with, you've got your average power and your inductive reactance, and you can add in a capacitor that can completely cancel that. If you would be able to add in a capacitor that can completely cancel that, you would actually end up back to a purely resistive load from the perspective of your source. So this is how you want your source to see things. And by the way, if you think about what we've done in terms of our circuits, we've always talked about the resonant frequency. That resonant frequency theta squared equals 1 over LC. Well, in fact, if you use your resonant frequency and you set up the right capacitors, That's essentially what you're doing when you do this power factor correction, except it's easier to do the math in this case because you don't have to worry about actually figuring out what the complex impedance is of your entire load. You very simply look at it from the perspective of the source, and you take a look at the complex power that's being used by your load, and you subtract off by doing the opposite on the other end. Now, what we've done here is I continue to shift these over, so this is now a capacitive load. How do we know that? Because the difference in that angle is negative. So now what you actually have is a situation where phi I is greater than phi V, and as soon as phi I is greater than phi V, you're, instead of doing what you did before and lagging, your voltage is actually leading. So your voltage is ahead. So now your voltage is leading. You see that angle right in here, and you see that there becomes an imaginary part. So this is starting to drop again. And it works in the opposite direction. As you drop even more, this gets lower, until you get to a purely capacitive load. So this is purely capacitive. That means there is a 90-degree phase shift between here. The voltage leads. And once again, your power has a zero average. So average power is zero. And this is again the situation where you have something purely real, but in this, purely imaginary, but in this case, purely imaginary in the negative sense. So ZL is going to simply equal to minus J times X. These graphs teach us a lot about power. The more out of phase the voltage and current are, the less average power the system can use. We also see right away that power is something that has double the frequency of the actual system voltage and current. And we see that we can fix what's happening in a system by fixing the power that the different elements are absorbing. The system's magnitude of the voltage needs to increase if we have too much of a phase shift, and so we can actually adjust that by playing with what happens to the power. And you can actually see that directly from the graphs and from the instantaneous power. And in order to correct what you want in a system to minimize the amount of power that you need to use, you correct this simply by keeping the voltage and current as close to in phase as possible. That gives us the largest average power. So if we don't want to waste the power that's being provided by the voltage and current, we want to make sure that the power has the largest average possible. In order to do that, we want to sync up the phase as much as we can. And that concludes everything that we need to in terms of AC power. So we've actually now finished unit number 2, and what we're going to be starting in our next lecture is part 3 of electric circuits, where we look at various different elements, either powered elements or nonlinear elements. We're going to look at dependent sources first, and then op-amps, diodes, BJTs, and MOSFETs. And we're going to get just a little bit of a flavor of an introduction of what each of these things can do for our electric circuits. Thank you and have a great day.